Hi everyone. So we are delighted to have Alex visiting Brown today and give a talk. Alex is an assistant professor in Boston University, and interestingly, he takes both physics and computer science PhD students. His work lies in both quantum computing and cryptography, where he both tries to create objects in the quantum settings, such as the pseudo-random functions in the quantum settings, and also tries to attack classical problems using quantum, such as this work today. So yeah, without further ado, let's welcome Alex.
Yeah, thank you so much for inviting me. Really happy to be here. This is my first time at Brown. I've not been here before, but it's been a really fun visit so far. Yeah, so thank you so much for having me. So today I'm going to be talking about this new work. It's not out yet, but we'll post it very soon. I do have a paper that's ready that I can send to you if you're interested. But it's brand new work with two wonderful collaborators, Islam Faisal, who's at BU. He's a student of mine, and Anand Natarayan, who's at MIT. I wanted to pick a topic today that's sort of accessible to a general CS audience. It's going to be a quantum talk, but I'm sure most of you are not super familiar with quantum computing. Is that right? Can we do a quick show of hands? Who of you has some familiarity with quantum computing? Okay, great. Okay, cool. So even if you don't, I hope the talk will be somewhat accessible to you. So the topic is sort of constraint satisfaction problems. In CS, we work with constraint satisfaction problems all the time. They appear all over the place. We have things like Boolean satisfiability or map coloring, but CSPs also capture, really fun sort of games, that we, play recreationally. But CSPs are, also really interesting. In the real world, if you get new speed ups for certain important problems, that will save people a lot of money. So, we care about CSPs, not just because they're fun, they're also really practically important. Okay, so what is a CSP abstractly? So, roughly this is what I have in mind. So we're going to start with sort of the classical picture, and then I'm going to talk about, how this relates to quantum. And so that's sort of the goal for today. So abstractly, I want to start with the definition of a K-CSP or a K-local CSP. Okay, so abstractly, what I have in mind is I have a bunch of variables, x1 to xn. They can take, say, Boolean values. And then I also have constraints. Okay, so these constraints sort of indicate, which of these variables or which subset of variables, my constraint is over. And a classic example is 3-SAT, very classic problem. We have sort of 3 local constraints that act on 3 variables at a time. And obviously, the goal is to say, satisfy, these constraints at the same time. Okay, so when we work on CSPs, there are basically 2 questions that we, care about or that we want to know the answer to. If I give you a CSP, like a Boolean formula, first question is it satisfiable? And the second question is, how many of these constraints can I actually simultaneously satisfy? Okay, so these are like classic questions that we, care about, that we want to solve, that we want to understand. And yeah, it turns out that these kinds of questions, even though they sound pretty harmless, generally correspond to NP-complete problems where we don't have any efficient algorithms. Okay, 3-SAT is a classic NP-complete problem. Okay, so that just means basically we have no good algorithms, and in the worst case, these problems are really, really hard. Okay, so what I actually want to talk about today is sort of the quantum or the quantum version of a constraint satisfaction problem. Okay, so it's going to be somewhat light on the quantum side, I hope, and accessible to you if you've never, seen quantum talks before. But basically, the gist is that quantum constraint satisfaction problems also appear all over the place. So in areas like quantum physics or chemistry, there are so many quantum versions of constraint satisfaction problems that we would like to solve. Okay, and typically these have to do with like actual physical systems, like actual molecules. Yeah, so an example here is the hydrogen molecule. Okay, it's a very simple molecule, but if you're a physicist or a chemist, what you care about is, like what is the binding energy of this molecule, for example. So typical question is, if I see a molecule, I would like to know, what are the low energy states, or more specifically, what is the ground state of the problem? Okay, so the ground state is the state of least energy. Okay, and if you characterize a physical system, then you can argue that there is always such a state of low energy, and how do you find it? Okay, it turns out this is also kind of a constraint satisfaction problem. Okay, so if you have a description of a physical system like hydrogen molecule, then it's a physical system that obeys certain physical constraints. All of these are known, and the question is, which state sort of has the minimal energy here? And yeah, in the hydrogen molecule, this would correspond to, for example, the binding energy. You can imagine, if the nuclei are too far apart, that affects energy. If they're too close, they repel each other because they're positively charged. And simultaneously, these nuclei are, also feeling a force because of the electron, which is negatively charged. And, there are lots of constraints. You're trying to minimize and find the smallest energy. That's a constraint satisfaction problem. Okay, it's just a simple example, but they do appear all over the place. Okay, so what's really different about quantum versus classical? So here is sort of a helpful dictionary. If you don't know anything about quantum computing, however, you're a computer scientist, you have a rough idea what a classical constraint satisfaction problem is. Here's like a really helpful way to sort of map what you know to how things look in a quantum setting. Okay, so what's the analog of a variable in the quantum setting? Well, the analog of a variable is really something called a qubit. Okay, the simplest sort of quantum mechanical two-level system is a qubit. For example, like a spin that has two discrete values. It's either up or down. Okay, and these are sort of the quantum degrees of freedom, similar to variables in a classical CSP. Okay, so what are the analogs of constraints in a physical system? So these are now given by Hamiltonian terms. Okay, so this is, if you're a physicist, then you're well familiar with Hamiltonians. If you're a computer scientist, maybe not so much. But roughly speaking, these are sort of like the quantum or physics analogs of constraints. The Hamiltonian sort of captures, the physics of a system. It characterizes the interactions and so on. So, this is naturally where the constraints show up in a physical system. Okay. What about assignments? Well, an assignment is basically like, the values that you, enforce on your variables. Okay, in the quantum world, these are now quantum states. Okay, so these are sort of like, linear combinations of these degrees of freedom. Turns out that a quantum state is not just 0 or 1. It can be a, complex linear combination of these two degrees of freedom. Okay. So already you can see that quantum constraint satisfaction problems are a little bit richer than classical, right? Now, they're not just like Boolean assignments. You can actually have quantum states, and you're trying to find out, how do I pick these amplitudes or these coefficients in such a way that I, solve my optimization problem. Okay, so quantum states are richer. You can have linear combinations of 0 and 1. There are many ways to potentially satisfy such a constraint. And so, yeah, it's a much richer landscape. Okay, so if you think about CSPs, then often a question is, how many constraints can I satisfy? So ideally, you want to minimize the number of unsatisfied constraints. Okay, in a quantum world, the natural analog is minimizing the energy. Okay, so now you're asking, which assignment has the lowest energy, and this is a very useful question in physics or chemistry. And then the optimal assignment is sort of the ground state that has the lowest possible energy. Okay, so roughly speaking, this is sort of how you map the classical to the quantum language. Is that sort of clear, or do you have any? Yeah.
Is there an analog to satisfied versus unsatisfied? Would that be zero energy?
Yeah, it's a good question. So, in the quantum world, the distinction between satisfied and unsatisfied is not very clear, or not very precise. So, it's not really either or. You can be sort of in the middle. It's like a more continuous sort of world where you can, you can satisfy constraint a little bit, but you're violating it a little bit, but not fully. And it's a much more continuous sort of picture. So yeah, we'll see what exactly that means, but yeah, it's a bit fuzzy. Yeah. Yeah.
Should I think of this as strictly generalizing classical CSPs, or now that I'm allowed to do continuous things and
yeah,
easier?
It is absolutely the case that classical CSPs are like a special case of the quantum picture. Like it's a you can write down a specific Hamiltonian that yeah, it completely includes a classical CSP. And then quantum generalizes everything much more. Yeah, but the classical is a purely special case. Yeah. Yeah, so you can think about it as continuous CSPs, but with quantum surprises, and we'll talk about them. So yeah. Okay, so I hope this was useful. So now we sort of laid a common language here. So when I talk about energies and ground states, I hope you can sort of map this onto something that you're more familiar with. Okay, so let's actually talk about a concrete quantum example that's that sort of naturally inspires sort of a constraint satisfaction problem. Okay, so I mentioned that these CSPs in the quantum world take place in actual quantum systems. Okay, what's a simple quantum system? We're not going to talk about molecules. We're going to talk about very simple, sort of well-described systems. And one example is a system of n interacting particles. Okay, each particle is a spin. It can be up or down. Now you have n such particles. Okay, and these are allowed to interact. Okay, so think of them as like quantum magnets. Okay, so depending on what side of the magnet you're on, magnets can sort of repel each other and so on. So there's a quantum analog of this kind of interaction, okay? And so these spins are sort of like quantum magnets, and depending on whether they're up or down, they can bias each other towards like a higher or lower energy state. Okay, and this is called a 1D spin chain, okay? And the physics of the whole system are described by something called a Hamiltonian. Okay, and the Hamiltonian captures all of the interactions between the particles, okay? And in particular, it also describes the allowed energies of the system, okay? So, depending on what spins I have here, the Hamiltonian will tell me, what energy do I assign to this specific configuration of the system, okay? So in quantum notation, we write the Hamiltonian as basically a sum of other matrices, okay? So H here, the Hamiltonian, is a huge matrix. It's a 2 to the n by 2 to the n matrix, okay? Very big matrix. And this matrix contains basically all of the interactions, and the sort of spectrum of this matrix corresponds to the energies of the system. So they're discrete, and there are many allowed energies. And depending on what spin assignments I have here, the energy can either change. It can be low, or it can be a high energy or a low energy configuration. Okay, and these are also matrices, but the catch is that these matrices are sort of localized. Okay, so this here is an interaction between, say, the ith and the I plus first particle. Okay, and it's kind of like a spin-spin interaction. If the spins are aligned, that can have consequences for energy. If the spins are not aligned, that can have another consequence. So, these kind of spin-spin interactions are captured here. And here is another term. So this is the Pauli X matrix. This is the Pauli Z matrix. Okay, the Pauli Z matrices capture spin-spin interactions. And the Pauli X matrix is kind of like a spin flip operation. Okay, this is kind of like a NOT gate in a logical circuit. Okay, so this X gate can flip the spin from up to down, or down to up. Okay, and this also carries sort of an energy, with it. Okay. So roughly speaking, this is what like a simple sort of, quantum system on n particles looks like. Okay. And now, what is the actual like constraint satisfaction problem here? The task is to minimize the energy. Okay. So now here's our classic, quantum constraint satisfaction problem. You have a bunch of spins. All of them can be up or down, or they can be combinations of up or down. Okay, so here you have a superposition of up and down. Here you have a superposition of up and down, and so on. Okay, and depending on how you assign your qubits here, the energy will change. Okay, and what is the energy? It's sort of this like sandwich between the quantum state and the matrix as an operator. Okay, so think of this as like matrix multiplication, where you have like a row vector here. Okay, here you have a huge matrix, and here you have a column vector. Okay, this is just the notation for a quantum state. And if you compute this sort of sandwich between the operator and the state, you get an energy. Okay, and this is always a real number, and you want to minimize this real number. Okay, so depending on how you assign your quantum spins, this energy is like small or large. Okay, so this is the problem here. And the goal is to really minimize this energy to pick a low energy configuration. Okay, and this tells you obviously something really useful about the physics of the system. Are there any questions about this simple model? It will not get more physicsy than this, I promise. Okay. Yeah.
So this is the goal. What are the constraints?
Yeah, the constraints are sort of like here in the sense that you're sort of trying. Okay, so this is a sum of matrices. Okay, and these you can think of as the constraints. Okay, so ideally you want to pick like assignments that sort of have like a low energy eigenvalue with all of these constraints at the same time. Okay, so roughly these matrices here are the constraints, and they are local in the sense that these constraints always refer to like at most 2 particles at the same time. Okay, so when I say k CSP in the quantum setting, this would be like a 2 local quantum CSP, because these constraints always refer to pairs of particles at the same time. Okay, so kind of like 3-sat, where you have like 3 variables in each clause. Yeah.
For my own understanding, like if I wanted to enforce that the quantum analog of my variable is being 0, 1, or I guess if I wanted to force all the qubits to be 0 or 1 and not a linear combination, how do I do that with this as this is my constraint? Or maybe the answer's not short.
Oh, like could I like assign classical values to my spins? Like forget about linear combinations. You're saying I'm going to put 0, 1, 0, 0 here and so on? Or
I guess, I'm saying like if I wanted to encode a regular CSP as a quantum CSP, I assume...
This is exactly what would happen. So then you don't have to worry about linear combinations. You can show that once you have a classical CSP encoded in a Hamiltonian, you can show that the ground state or the minimal energy is satisfied by a quantum state that's literally like a deterministic assignment of bits. You can prove that is the case.
But it's not obvious, I guess.
It's not obvious, but it's not hard to see if you're familiar with like what these matrices mean. It's not hard to show. Yeah. So and then you can sort of see why CSPs classically are a special case of this. You take out the superpositions. You remove the quantumness from these interactions in a certain sense, and then you get k-CSPs. But we'll see what that actually means. So general theme of my talk is like, how are classical CSPs different from quantum CSPs? Okay, and I want to like really like point a finger on where exactly they differ, and that's sort of the goal of this talk. Okay, so here's the sort of formal definition. I apologize if there's a lot going on here, but this is sort of the formal definition of a quantum constraint satisfaction problem. Okay, it's basically the more general version of what we saw on the previous slide. Okay, so you're given as input a Hamiltonian. You can think of it as like, a description of the constraints of the system. Okay, so the Hamiltonian is capturing all the constraints. Okay. And this is an n-qubit Hamiltonian. Okay, so you have sort of n-qubit states that you have to optimize over. You have many constraints. Okay, And so m is sort of like a polynomial in the number of qubits. Okay, each Hamiltonian term, okay, is like a linear operator that acts on at most k qubits. Okay, it's kind of like the quantum version of a clause. Okay, and now you have a decision problem. Okay, this is the simplest possible kind of computational task here. The decision problem is, given the Hamiltonian, I have to decide, is the ground state energy small, meaning the energy is less than A for some threshold, or is the ground state energy large, meaning it's at least B, okay? And A and B are sort of separated. Okay, so it's a promise problem. I give you an instance where I promise you that it's either less than A or at least B, okay? And you have to solve this simple decision problem, okay? So this is like something called the k-local Hamiltonian problem, basically the natural analog of a CSP in the quantum world. Okay, so what do we know about this problem? So 3-SAT is NP complete, or general k-CSP problems are NP complete. This problem, quantumly, is complete for sort of the quantum analog of NP. Technically, it's a quantum analog of this class MA. I don't know if you are familiar with it. Sort of like NP, except that the verifier can be correct with probability 2/3 or with probability 1/3. Okay, so this is called QMA, Quantum Merlin Author. Okay, so QMA is a class that contains NP, so it's a strictly bigger class, and we believe that NP and QMA are distinct. Okay, so QMA is like strictly larger. We believe that's the case, but we don't know for sure. So the landscape looks something like this. Okay, so here we have P and NP. Okay, we know that many KCSPs are actually complete for NP. Okay, then we have QMA, which contains P and NP, but it also contains BQP, which is sort of the quantum analog of P. Okay, so BQP is like polynomial time quantum computation. Okay, and QMA is like containing all of these. As far as we know. Okay, it definitely contains NP, but we believe that they're strictly separate. Okay, so this is roughly the complexity landscape. So quantum problems are potentially much harder than classical constraint satisfaction problems. Okay, so the general theme of my talk, so where I want to go next is, where exactly do these CSPs differ classically and quantumly? Okay, so we have like our canonical NP complete problem, which is 3-SAT. We have our canonical QMA complete problem, which is the local Hamiltonian problem with locality 2. Okay, so 2 local Hamiltonian problem is complete for the quantum version. Okay. So these are sort of the canonical CSP problems on the classical and the quantum side. Okay, then you can ask, what exactly is going on sort of in the middle or at the boundary of these two? Which problems are like sort of a little bit classical and sort of a little bit quantum? Okay, so we want to better understand what the hell is going on here, and these are like useful problems to really work on because. If you identify problems that are sort of at the boundary, then this tells you something useful because it tells you that certain quantum constraint satisfaction problems are much more classical. Okay, and that's good news because if quantum satisfaction problems are more classical, then you can use classical techniques to solve them. Okay, so naturally we're interested in like which of these problems are secretly more classical than others, and then we can use classical techniques, and this is really useful to know. Okay, so this is sort of the inspiration for our work to better understand how classical and quantum is sort of different from one another. Okay, great. So this brings me to our work. So before I talk about our results on this theme, I want to briefly talk about what was known before about this boundary. Okay, so we didn't know that much. Okay, so in order to understand, what exactly is in the middle, what is exactly, sort of classical and also quantum at the same time, which problems are sort of intermediate between classical and quantum. And to motivate this, we have to basically review what's different about classical and quantum information processing to begin with. And a natural way to understand what's different about classical and quantum is to talk about basic facts about matrices. Okay, so who of you has seen the commutator before? Great. Okay, so if you talk about the commutator, it's like a very simple object, but it already reveals quite a lot about what's different classically and quantumly. Okay, if you're like an applied mathematician, then you may have observed, that matrices or matrix multiplication doesn't commute. Okay, A times B is technically not always B times A. And if you're a mathematician or a computer scientist, maybe you think, okay, so what? Yeah, these don't commute, but why should I care? So if you're a quantum physicist, then the fact that certain matrices don't commute is actually kind of a profound statement, and actually has physical implications that are really important. In quantum physics, the fact that certain matrices or operators don't commute means that certain measurements cannot be carried out simultaneously. Okay, so somehow like observing certain facts about a quantum system is sort of incompatible with observing another fact. Okay, and all of this quantum weirdness is sort of captured in the commutator. Okay, so basically certain operations don't commute, certain observables cannot be measured at the same time. Okay, and if the commutator is 0, then we say that A and B commute. Okay, so if A and B commute, then the quantum weirdness sort of disappears a little bit, and things are at a very rough level more classical than quantum. Okay, and standard math fact, I'm sure many of you have seen this before. Commuting matrices actually have this nice feature that they're simultaneously diagonalizable, meaning that there's a preferred basis in which both A and B are diagonal. Okay, so a very cute math fact that's very important in quantum physics. Okay, so what I want you to remember is that whenever matrices commute, they behave more classical rather than quantum. Okay, and it turns out that this simple observation has already told us quite a lot about how classical and quantum CSPs differ. Okay, and there was a prior work that sort of tries to capture this difference. So they studied a version of the quantum CSP problem called the commuting k-local Hamiltonian problem. It's basically the quantum optimization problem, except that you enforce all of the constraints to commute. Okay, so now the constraints commute. I said that things become more classical. And that is indeed the case. Okay, so if you replace these constraints with commuting constraints, then this quantum optimization problem becomes much more classical. Okay, and in fact, the optimization problem is much more like a classical CSP. Okay, the fact that things are commuting makes it much more like a classical sort of satisfiability problem. Okay, somehow like the commuting constraint, or this additional commuting constraint sort of takes the quantumness out of the problem. Okay, and this was observed in a prior work from like roughly 20 years ago, and we've known about this feature. Okay, and so this is kind of a nice observation. It tells you that a lot of the quantum hardness is captured by non-commuting constraints. And so here's what people observed. This was Bravi and Viali in 2004. They noticed that if you take this quantum constraint satisfaction problems, but you add this commuting constraint, it actually takes you all the way from QMA into NP. Okay, so somehow like adding this commuting structure makes the problem an NP problem. Okay, it's not NP complete, but somehow this like optimization problem falls into NP. Okay, it's captured by a classical complexity class, which is kind of surprising to people. So this suggests that the moment your constraints are commuting, they're much more classical, and the complexity is described by a classical complexity class. Okay, so that's kind of fun. Yeah?
Maybe you described this before, but
yeah.
When you, in order to be able to solve this, right? So my understanding right now is that the instances quantum, right? But the fact that you can solve it.
Okay, so this problem, even though it has some like quantumness in it, is actually a classical input, classical output problem, right? So the input is a classical description of this Hamiltonian, purely classical. It's a string that represents, these quantum constraints. And the output, remember, is also classical. You have to say yes or no, right? But it's what you're bringing up is a really good point, because this always makes people wonder, like, how come you're talking about these quantum problems and they're in NP? How can that be? Like NP is a classical class, and this is why, because it's a classical in, classical out problem, but some of the problem itself captures something quantum mechanical. Okay, so this is why it's possible for like this restriction to actually be in NP, even though it describes a quantum problem. Yeah.
I have maybe a silly question. Didn't you say the size of the Hamiltonian is like 2 to the n?
Yeah.
So
Great. That's like, first this confuses people, and then this like the next question that people ask. How come like the input is like an exponentially large matrix? So the cool thing about this, like a classic thing that people always wonder. So the thing is, like, this Hamiltonian is a 2 to the n by 2 to the n matrix, where n is the number of qubits. But actually, these constraints here, h sub I, okay, only act non-trivially on at most k qubits. Okay, so each constraint is technically sort of a constant size matrix. Okay, everywhere else it's sort of acting as the identity. Okay, so you can literally list, these like constant size matrices, and they sort of implicitly describe this huge Hamiltonian. Okay, so you'd never have to write out the whole Hamiltonian. It's sort of implicit, but actually, if you were to compute it, it would have dimension 2 to the n by 2 to the n. But it's succinctly described by just constant size matrices, and you have m of them. Okay, so this is sort of like the length of the input. It's not actually like exponential in itself. It has a compact description.
Can I ask another question, which is, formally, what does it mean, like, as far as the matrix is concerned, to act on at most k qubits? Like,
yeah, it's basically, in 3SAT, these clauses refer to like, 3 variables at once, right? All the other variables are not referred to, right? So it's similar here. It's like a local interaction, even though, it's technically like an interaction on all qubits, but it's localized. It only acts non-trivially on a few qubits at once. Everywhere else is acting as the identity operator, but technically it's still like a large object. Yeah.
It's not necessarily the case that it's a sparse matrix, for instance, or?
So in the classic formulation of the problem, it's always a k-local Hamiltonian, and k is always a constant. So yeah, it's a constant size matrix.
Or like only a constant subset of the 2 to the n entries are not 0, is what you're saying?
Yeah, you can think of it as if you wrote down each of these constraints, it would be a 2 to the n by 2 to the n matrix where almost everything is 0, and a small like constant size corner of this matrix is a non-trivial. Yeah. Yeah.
Why is it not always an NP problem? Because you
Yeah.
can always verify this using like constant.
Oh.
If it's a yes instance.
Right. Okay. So, right. So you're asking basically what's what's the difference about the witnesses here and here, or
Like for example, the yes. If it's a yes instance,
Yeah.
and I give you a description of this quantum.
Okay. So then that's a good point. So a quantum state doesn't have a succinct description. Okay. So the witness here, you can technically represent it as a classical string, but it would be a 2 to the n length vector. Okay.
Oh, it's
So-
not just.
Yeah.
I see. I thought it's like you have n qubits and every qubit is alpha beta.
Yeah.
It's not. It's like.
So, okay, this is a really good point. This often when I teach quantum computing, like people find this really confusing. But each qubit is sort of alpha plus beta. But a general quantum state can have amplitude, has 2 to the n amplitudes across all combinations of assignments. Yeah. So that's why it's psi here is a length 2 to the n vector. Okay.
But then interestingly, when h are all commute,
Yeah.
then it can be represented.
Great.
using polynomial.
Yes, and this is a very non-trivial result. But if these constraints commute, then there's sort of like a very classical or clever classical sort of piece of information that you can hand to the verifier. That's, you know, that's not a quantum state. It's a classical object. That's enough to verify this energy thing. Yeah. It's yeah.
Oh, yeah. Okay. Wait. Maybe I'll reveal how little I know about quantum.
Yeah.
But like, so is it the case that if the optimizing quantum state for this is such that none of the qubits are entangled, then it's easy to verify in polynomial time?
Yes. Then there's a product state representation that's that you can write down much more efficiently. Yeah.
But then, okay. So then my follow-up question is, in this case where all the Hamiltonians commute,
yes.
Is it necessarily the case that the optimizing quantum state it has?
No.
Okay.
Yeah. So it can actually still be an entangled state that doesn't have an obvious short representation, but there's still a clever way to you know, hand the verifier a witness. Yeah. Okay. But all of these are very non-trivial results, and this Bravi-Viali result is like a genius paper. I don't know how these guys came up with it, but you know, the fact that this is an NP requires, you know, lots of math that has to do with C-star algebras, and like, you know, very like crazy representation theory that, yeah, I don't know how these guys knew about this field, but yeah, so this statement here is very non-trivial. Yeah.
I had another question. So you said it's an NP. Is
Yep.
it know whether it's NP complete or?
We don't know if it's NP. I think we believe it's not NP complete. Yeah. So it's so I put these like black circles around the complete problems, and this is just contained in NP, but not believed to be complete. Yeah. Yeah. Thanks for the great questions. All these are really good questions. So yeah. Okay. So finally, our work. I'm almost out of time. So okay. So here's the landscape. We know about this sort of relaxation that makes the problem almost classical, or at least, you know, contained in NP. What we wanted to find is a problem that's like really on the boundary. So depending on how you wiggle the problem, you're either in this world or in that world. Okay, so we wanted to find really, you know, a problem that's right on the boundary. So you wiggle it a little bit, becomes quantum. You wiggle it a little bit, it becomes classical. We like really wanted to point a finger at like what's exactly on the boundary. Okay, and we find a natural sort of quantum CSP that has this property. And we call it the almost commuting Hamiltonian problem. Okay, not super far-fetched. You know, you have something that's commuting, takes you here. What if it's like slightly non-commuting? Okay, and surprisingly, no one has studied this problem before. We found it supernatural. Okay, so we take, instead of commutators that are 0, we ask what if the commutators are slightly non-zero? Mathematically, you know, the commutator applied to these matrices is still a matrix. You can take its norm, okay? And we say, what if the norm is like small, okay? And now, depending on what epsilon is, you know, this can be, you know, almost commuting or like far from commuting, okay? So yeah, you had a question?
Yeah, I was just, when you mentioned norm, I was just wondering what kind of norm specifically?
Oh, this is going to be the operator norm. So think of it as like, yeah.
Do you take the trace or?
No, oh no, so this is basically take, it's the maximum over all vectors of norm 1 that you hit this matrix with. So it's like max over all vectors of norm 1, and then you like take like this operator times the vector, and then the maximum, L2 norm of this, yeah. But again, good question. Yeah, it's there's so many norms, and in quantum you have to be careful which norm you're talking about. But this is the natural one, the operator norm for operators. Yeah, great question. Yeah. Okay, so this is what we wanted to study. Pretty simple idea: make things almost commuting for a tiny epsilon. Okay, and see what happens. And these almost commuting systems are actually physically interesting. Okay, there are many examples of systems that are nearly commuting. And it's kind of good motivation because in the real world, these commuting Hamiltonians are actually pretty rare. Okay, so physical systems are rarely commuting. Okay, so in the real world, things are messy. You know, things anti-commute, and we wanted to sort of bring, you know, these quantum CSPs closer to the real world by like making things nearly commuting, which is much more realistic. And we give some examples in the paper of actual physical systems with this property. Okay, so the question is, what happens if you put an epsilon here? Okay, and not surprisingly, depending on how small epsilon is, it can either, make your problem fall into NP, or it can like accidentally end up outside of NP. Okay, so great. So here's sort of the comparison. Okay, this is the commuting Hamiltonian problem. All the commutators are 0. This is the almost commuting problem. All the commutators pairwise are small. Okay, for some epsilon, which is part of the problem. Okay, and now the question is, what happens if you add epsilon? First observation is, if epsilon goes to 0, it takes you back to the original problem. Okay, so you might, conjecture, well, if epsilon is like really, really small, okay, then my complexity of the problem should behave more like this, right? Pretty reasonable intuition. Okay, so you would expect that, if epsilon is really close to 0, like vanishingly small, then this problem should behave more like the commuting Hamiltonian problem. Okay, therefore, if epsilon is very small, it should be in NP. Okay, but if epsilon is like large and non-trivial, okay, then you're really in QMA land, because many sort of natural QMA complete families of Hamiltonians have exactly a constant epsilon. Okay, so this is roughly what you would expect, intuitively, and we show that this intuition is, is well-founded. So we show that if you take this problem at the boundary and make epsilon small enough, okay, it actually goes to 0 asymptotically in the number of constraints. Okay, so if epsilon sort of scales inversely with the number of constraints, then we show that this problem at the boundary gets sucked into NP, okay, which is kind of what we expected, okay, and that's our main result. But if epsilon is sort of more like a constant, then we have QMA complete Hamiltonians. Okay, so this problem is really at the boundary. If you wiggle epsilon, you end up here. Otherwise, you end up here. Okay, so this is kind of what we observed. Okay, so how do we show NP containment? Okay. Now things become hopefully interesting, okay, and this is where our techniques come in. Okay, so what do? We show that if you have an almost commuting Hamiltonian, then there's sort of like an iterative rounding procedure that allows you to find nearby commuting matrices. Okay, kind of a natural idea, right? If something is almost commuting, try to sort of map it onto something that's commuting but nearby. Okay. That's the whole idea behind our approach. Okay, so mathematically, the task is something like this. So this is kind of a toy version of the problem. But let's say someone gives you epsilon almost commuting matrices. Okay, so you know that they nearly commute. Okay, can you find matrices A hat and B hat which perfectly commute but are still close to the original matrices? Okay. For some function delta, say, that goes to 0 if epsilon goes to 0. Okay? Yeah?
Is the result assuming anything about A and B, like the gaps for the energy?
Okay, great. We will have to assume a lot of a lot of spectral properties. Otherwise, none of this works. But yeah, that's a great intuition, and I'll talk more about what we assume. Okay? So so I'm sure all of you would agree this is like a pretty, reasonable natural problem in math. And naturally, this has been studied. Okay, people have written papers about this sort of rounding idea. Okay, so what do we know? We know that this kind of rounding is possible if the matrices A and B are Hermitian. Okay, meaning that their complex conjugate, their conjugate transpose of the matrix is equal to the matrix. Okay, so for Hermitian matrices, this is actually possible. There are such matrices that you can find that have this property, okay? And we even know bounds on delta, okay? So for Hermitian matrices A and B, this is pretty well understood, okay? Here is like the surprising downside. Once you have triplets of matrices A, B, C, this doesn't work at all, okay? So there are no-go results. There are like counterexamples that they're pretty contrived, but mathematicians have found them. Okay, so in general, the problem is actually impossible once you try to round multiple matrices. Yeah?
Do you have good examples of deltas that we use now to kind of round the
Yeah, so these deltas scale with the size of the matrix. You know, if the matrix is d by d, then delta somehow depends on d, and also on epsilon. I don't remember at the top of my head what they look like, but I'll show you what we get later. Okay, so this is kind of a strong barrier, right? Because if you think about it, we actually, we don't just round pairs of matrices. We have m many Hamiltonian terms that are all pairwise almost commuting. We actually need to round many matrices at the same time. And there's an impossibility result that says, actually, you can't even do 3. Okay, so when we started out, we thought, oh, man, okay, so it's kind of a cute idea, but that's just not going to work, because this impossibility result says that you can't round triplets of Hermitian matrices, and we have Hermitian matrices. So, you could imagine just giving up, right? Like this somehow seems futile. Okay, so here is how we managed to get around it. Okay, so we crucially have to exploit the fact that our Hermitian matrices are not just any generic Hermitian matrices. These are actually, physical constraints that have sort of physical properties that generic Hermitian matrices don't, right? So we really avoid these no-go results by using the fact that our constraints are, local. They are non-trivial, acting non-trivially at only few particles at once. Okay, you can imagine it's a huge matrix that's sort of like 0 in most places and only in a small corner that's constant size, something non-trivial happens. Okay, so we exploit locality, and we also exploit that these matrices act on qubits which have sort of like, which are 2-level systems, so they have a small local dimension. Okay, so it turns out these two physical constraints really allow you to get around this generic impossibility results. Okay, we really exploit both of these in our technique. Okay. Okay, so here's what our rounding technique does in a nutshell. Let's say I give you an almost commuting Hamiltonian. Okay, it refers to particles that interact. So you can, imagine that you have sort of a lattice. Each vertex is a particle, and you have edges between, neighboring particles. So each edge is an interaction. Okay, you can imagine these particles are spins, and these edges correspond to spin-spin interactions. Okay, so we take an arbitrary Hamiltonian with m terms and have the condition that the terms almost commute. Okay, so you can imagine that these interactions involve pairs of qubits. Blue and red, for example, are two separate interactions. And you know that these interactions almost commute. So there's some epsilon here that sort of captures how non-commuting they are. Okay, so this is our starting point. Then our technique says, given this Hamiltonian, you can round it to another Hamiltonian, h hat. Okay, and h hat is now exactly commuting. So all of these commutators are 0. Okay, this Hamiltonian preserves the locality. Okay, so if the blue box previously referred to these particles, the rounded blue box once again refers to these particles. So it preserves locality. Okay, so if this is too local, then this is too local. Okay, all of the localities are preserved. We basically just wiggle these interactions to something that's nearby. Okay, so this is what we do. Okay, is this clear? So this is roughly what our technique achieves. And obviously, if this is epsilon, then the nearby Hamiltonian is sort of delta of epsilon away. Okay, and this delta depends on the initial epsilon. So this Hamiltonian is sort of close to the original Hamiltonian as a function of epsilon. Okay, we derive this epsilon dependence. Okay, so here's the high-level idea. So I won't show you too many technical details, but I will give you sort of a taste for how this works based on a very simple example that's already non-trivial. So remember I showed you, or I told you that triplets of Hermitian matrices cannot be rounded. Well, here's a triplet. Okay, you know that the generic rounding cannot work, but we will actually round this specific triplet. Okay, so it's a Hamiltonian on 3 qubits. Okay, so it has 3 interactions. So the first qubit is here. There's an interaction that involves, or this qubit is acted on by this Hamiltonian term because 1 appears here, And there's another Hamiltonian term, 1H3, that also talks to this qubit. Okay, so this qubit is sort of acted on by this interaction and this interaction. Okay, in total there are like 3 interactions between all the pairs of qubits. Okay, and this is a simple triangle Hamiltonian. And let's imagine that this is almost commuting. Okay, so I have epsilons between all of the pairs. Okay, now given this simple triangle Hamiltonian, I want to find a nearby commuting Hamiltonian, okay, which has the same structure except all of the commutators are 0, okay, and this Hamiltonian should still be close. Okay, that's the goal. And I'm going to show you how to do this for the triangle. And not surprisingly, like spectral properties will appear now, because otherwise this can't work. Okay. Okay, so here's step 1 of how we approach this problem. Okay, step 1 is focus on one qubit at a time. So let's just pick this one. Okay, so this qubit is acted on by this Hamiltonian term and this one. Okay, it shows up in both of these interactions. Okay, the first thing we're going to do is take this qubit and look at its interactions that it's involved in and expand these interactions in a useful basis. Okay, so now I'm going to use a bit of quantum notation here, but it turns out that these interactions are matrices and they can be expanded in a natural orthonormal basis. Okay, and these are the Pauli matrices. Okay, it's like expanding a vector in a natural basis. Okay, here's how we do it. We expand these terms in a natural basis. Okay, so these terms each have an expansion. Okay, these are sort of like the basis vectors. Okay, and here I have linear combinations over specific sort of basis vectors. Okay, so this you can just do. It's just kind of like linear algebra. Okay, now we show that if these terms epsilon almost commute, then we prove that this implies that these coefficient matrices, okay, also epsilon almost commute. Okay, so why is this an interesting observation? Okay, here's how this is useful. So, there's actually some formatting issue here. So these matrices here are actually 4x4 matrices. Okay, so these are 4x4 matrices. But now, if I apply this result here, then I can conclude that the same almost commuting property applies to these matrices inside of the expansion. And these are now 2x2 matrices. Okay, so I've done kind of like dimension reduction. Okay, I can show that, instead of like rounding these matrices, it sort of suffices to round the smaller matrices and to stitch them together. Okay, so here's like a dimension reduction that has taken place. Now we've reduced the rounding problem to a smaller dimension. Okay, this is the first step. Okay, and now we have a much simpler problem. We have a 2x2 case where both matrices are 2x2. Okay, it's 2x2 matrices that epsilon almost commute, and we want to find nearby matrices also of dimension 2x2 that exactly commute. Okay, and not surprisingly, we now have to look at some spectral properties. Okay, we're going to do a case-by-case analysis. Going to focus on one of the matrices, say A. Okay, A is a Hermitian matrix, so you can diagonalize it and has a spectral decomposition. Okay, A can be written as eigenvalues times sort of eigenspace projectors. Okay, these are the projectors onto the respective eigenspaces. Okay, so any A that's Hermitian can be decomposed like this. Okay, the first case we study is, let's say the matrix is gapped. Okay, the eigenvalues are sufficiently far away from each other. Okay, this is case 1, which we call the gapped case. If A has this property, then all we need to do to get this here is to pinch B by the eigenspace projectors of A. Okay, this is actually a classic technique that shows up in many areas of math and physics. Okay, so you just pinch B by the eigenspace projectors of A. Basically, now the pinched B is sort of diagonal in the basis of A. Okay, so it turns out that if you just pick B to be of this form and let A hat to be A, this is achieved. Okay, we've just basically deleted everything that doesn't commute. Okay, and now A hat and B hat are exactly commuting. Okay, So we just deleted everything that's not so good. Okay? So if we do that, what error have we achieved? Well, you can show that if you pinch B, then the error you get is sort of quantified by the anti-commutation and the spectral gap of A. Okay? Very simple linear algebra, not hard at all to see. Okay? But now we see that there's an issue, because if the spectral gap is very small, meaning these eigenvalues are very close, this guy blows up. Okay? Not great. So we sort of have to threshold it and make sure that we control the spectral gap. Okay? So if the spectral gap is large enough, this is a good bound. If these are too close, then this technique is not great. Okay? But we have a fix. If the spectral gap is very tiny, if the eigenvalues are too close, we just do something else. We call it snapping. Okay? Now the matrix has eigenvalues that are really close to each other. What do we do? Well, if the matrix has eigenvalues that are very close, it's already sort of like an identity matrix. Okay? It's a multiple of the identity. Okay? So if we just let A hat to be the identity matrix times the largest eigenvalue, then this matrix is super close to the original matrix A. Okay? And again, the difference is tiny because the gap is tiny. Okay? But now we have a multiple of the identity matrix. The identity matrix commutes with everything, right? So voila, again, we were able to achieve this. Okay? So in either case, no matter what happens, we have a way to find nearby commuting matrices. Okay? So very simple linear algebra. And it turns out that you can sort of take the simple gap or snap approach and just iterate it many times. Okay? And then you can round all of these nearly commuting matrices at once. Okay? So we map this onto a graph problem. Okay? Each of these edges correspond to anti-commuting matrices. Okay? So these are sort of the vertices. We sort of cluster them into groups. Okay? Every time these anti-commute, there's an edge here. Okay? We basically want to make all of the edges green, which means everything commutes. Okay? And the way we do it, we sort of iterate this gap or snap approach. Okay? So we sort of pick a pivot element, and then we pinch all of the vertices here by these spectral projectors. We pinch all of the vertices here by these spectral projectors, and we iterate. Okay? And eventually, all of these edges will turn green. Okay? And then when you're done, everything commutes, and everything is still close by. Okay? There are a lot of technical steps here that I swept under the rug, but basically, this is what happens. Okay? And that's really it. This is our whole rounding algorithm. At the end, we get a commuting Hamiltonian, and we're happy. Okay? So this is all there is to it, and we just derive the bounds on how far this rounded Hamiltonian is from the original Hamiltonian. Okay, so now I'm almost done. I want to briefly talk about applications. Okay, so what can you do with this rounding technique other than show this new NP containment result? Okay, we actually give two applications of this technique. Okay, the first is quantum Gibbs sampling. Okay, so it turns out if your Hamiltonian is commuting, Gibbs sampling is much easier to do. So the Gibbs state is sort of like a thermal state of the quantum system at thermal equilibrium. Physicists love to compute it. If the Hamiltonian is commuting, it's very easy. Okay, our rounding technique helps you do that much more easily using classical techniques. And the other property, the other application is Hamiltonian simulation. If your Hamiltonian is commuting, then time evolution is much easier to estimate. Okay, so naturally, our technique allows you to do that for almost commuting Hamiltonians as well. Okay, so these are really two, nice natural applications for our technique. Okay, so I want to end here. Some open questions. So currently, our rounding technique only applies to 2 local Hamiltonians. Okay, can you extend the locality to 4 local? Okay, that would have more physics applications, so that would be nice. The other restriction is we only deal with 2-level systems where we have qubits. Okay, what if you have d-level systems, which are also interesting in physics? So then it means we have to extend it to qubits. Again, we don't know how to do it. Okay, and the last open question is maybe are there applications of this rounding almost commuting matrices in other areas of math or physics? Okay, so we believe this rounding technique may be useful in other sort of non-commuting optimization problems potentially. yeah, TBD. But that's, really it for me. So thanks so much for listening and yeah, for having me.
Are there any other questions for Alex?
So when describing the switch to looking at Hamiltonian data almost computing,
Yeah.
you mentioned the fact that generally in nature you do not get those Hamiltonian data perfectly. And I was wondering if there's some work that have looked at how they behave on the average. You kind of see how, what's kind of like epsilon on the average when you
So if I understand you correctly, you're saying currently the way we quantify this is sort of, we say the commutator norms are epsilon small for all pairs.
Yeah.
What if I relax this to like small on average? Is that what you mean? Or?
Oh, I guess more like if you just get a system of Hamiltonian, what will be the expected epsilon?
Oh, I see. It really depends. So the Hamiltonians that are, give rise to hard quantum optimization problems have a constant epsilon. Okay? So think of epsilon as typically being constant for like generic problems. Okay? Tiny epsilons show up in certain quantum mechanical systems. So here's an example. So actually the Hamiltonian I showed you all the way at the beginning is an example of such a Hamiltonian. So these matrices are diagonal, so all of these commute, okay? But now the z's and x's anti-commute, okay? You can show that they don't commute, okay? But the x's are weighed by a physics parameter called h, and h captures the strength of the magnetic field. So if the magnetic field is weak, then the commutator norm is order h, okay? So if the magnetic field is weak, then they are slightly anti-commuting. Okay, so this would be an example of almost commuting. And so epsilon here is h. So if the magnetic field has small strength, that means epsilon is small. Okay, so this really fits into our example.
Do you think the 1 over m out of 6 can be improved?
Oh, for sure, yeah. Yeah, we tried a little bit. Yeah, we don't know how to do it using our technique, but it's, I don't know, like 1 over m, for example, seems reasonable too. That it just, the epsilon scales inversely with sort of the system size or the number of constraints. I think that sounds like the right answer. But yeah, 1 over m to the 6 is the only result we were able to show, yeah. Yeah?
Is there one more quick question? So what takes it to QMA?
Constant epsilon. So if epsilon is constant, then we know examples of QMA complete Hamiltonians. So yeah, right now there's a bit of a gap, right? So for a very small epsilon, we're here. If epsilon is constant, like 1/2 or something, we are definitely in QMA land. Okay, so yeah, there's still a lot of space to explore, yeah. But yeah, I think it's interesting to ask, where exactly do problems become quantum rather than classical? And if it falls into NP, that's usually a sign that classical optimization techniques can help you. But if you're in QMA land, then you need a quantum computer to like optimize these problems. Yeah.
Regarding the rounding
Yep.
algorithm, so you mentioned that you will do this on pairs, right?
Yeah.
But the thing is, in the picture that you showed,
Yeah.
those pairs also interact with features. So
Yes.
what happens when you round?
Yeah, it's a great question. A very good observation. So somehow if you round, you can imagine you're like changing the matrices. So maybe suddenly, this amplifies, it changes the commutation structure with other matrices. That's absolutely true. Okay. So one thing we're exploiting here is something called transitivity. Okay. If A and B commute and B and C commute, then A and C must also commute unless B is the identity matrix. Then it's not true. Okay? So we're exploiting transitivity heavily here. And we also have some like robustness guarantees. So if we change remember, we're never changing these matrices too much. We only wiggle them a little bit to make them commuting. Okay, and we show that if we wiggle them a little bit, like these properties are like approximately maintained. Okay, and so yeah, you're absolutely right. There's a lot that can go wrong, but we do lots of bookkeeping that shows that we can, slightly change matrices without, breaking everything. And all of these are sort of robust. And if you do it carefully, you can actually, iteratively change all of the matrices slowly in a careful way, and then everything is commuting at the end. Yeah. Yep.
I guess if anyone has to go, they should go. But in your rounding, I guess it's always true that like one of the two matrices gets to stay the same.
Yes. Yeah.
Do you exploit that in iterating this? Or
yes.
That's not coincidental.
Yes, it's very important actually. This comes in one of our results when we in our analysis, when we calculate like distances and amplification of errors and so on, this fact actually comes in because one matrix is always unchanged, and this really simplifies the analysis like completely, and it's really crucial. So you can imagine a rounding technique that changes both matrices at the same time. It would be much more sophisticated than what we do, and it would potentially improve all of this, but we couldn't find such a technique. So somehow like global or a more global rounding is seems much harder. I don't know, the math somehow doesn't work out, or we haven't found any clever ways to do it. So it's easier to change one matrix at a time.
Let's take the speaker.
Yeah, thanks.